So the next topic is vapor-liquid equilibrium, and specifically vapor-liquid equilibrium between liquid and vapor of a single chemical or a single species. So I have right here just an example where we have liquid phase down in this region and we have vapor phase in this region. And this schematic diagram shows the interaction between the vapor phase and the liquid phase. So here in the liquid phase, we have all sorts of molecules that are in close contact with each other and they're moving around. Well, sometimes some of these molecules, they'll leave the liquid phase, they have enough energy to escape this liquid phase and get up here into the vapor phase. And once they're in the vapor phase, they can freely move about, just like all the gases can. And occasionally some of these gases or these vapor molecules may come in contact with the liquid and get absorbed back into the liquid. And eventually, if we let this sit over time, we'll get an equilibrium between the two so that some molecules are leaving the liquid phase and some molecules are entering the liquid phase from the gas phase. And when we do that, we have a vapor-liquid equilibrium. And all liquids have some sort of equilibrium with the vapor because at all times there's some sort of molecules or atoms on the surface that are leaving the liquid and entering into the gas phase. And we measure that amount, how much of that is coming into the gas phase based off the vapor pressure. So the vapor pressure is just the pressure which is proportional to the amount of molecules we have of the liquids that are entered into the vapor phase or gas phase. And so the higher the vapor pressure, the more molecules we have in this gas phase. The lower the vapor pressure, the less molecules we have in the gas phase. And so we want to be concerned about, again, this equilibrium between the two and how we deal with them and work with them when dealing with separations problems particularly. So here I have the example of the vapor pressure of water as a function of temperature. You see this line right here. And so what it's showing us is that as we go to higher temperature, the vapor pressure gets higher. And that makes intuitive sense if you think about what happens at higher temperature. At higher temperature, we're putting in more energy into the system, and since we're putting in more energy into the system, more of those molecules from the liquid phase can escape into the gas phase. So if we have more molecules in the gas phase, we have a higher vapor pressure. And at low energy or low temperature, not that many molecules are going to escape from the liquid phase into the gas phase. So the vapor pressure is low, like down in this region down here. Well, what happens here once we reach higher and higher temperatures? I've marked here a special point here as we go to higher and higher temperatures. This point right here that corresponds to 100 degrees Celsius, and if we read over here, 760 torr. Now, you may have realized, wait a second, that's the boiling point of water. Water boils at 100 degrees Celsius, and that is exactly true. So what happens as we go to higher and higher vapor pressure? Eventually, the pressure of the vapor above our liquid water reaches 760, and 760 torr is equivalent to 1 atmosphere. And if we go to higher temperatures, it gets even bigger. But the point here being is that once we've reached 760 torr, the pressure of our vapor has reached the pressure of the atmosphere. And at that point, what we have is our liquid itself starts to boil because the vapor pressure is larger than the pressure of the surrounding atmosphere or the surrounding typical surrounding atmosphere. So when we want to define what the boiling point of a liquid is, what we need to do is find out what its vapor, the temperature of its vapor pressure when it's 1 atmosphere, or in this case, 760 torr. And if we do that, that's what we define as the normal boiling point of a liquid, whenever the vapor pressure equals 760 torr, or 1 atmosphere. And so here's just an example of the water vapor pressure. What I'm showing you here is the vapor pressure as a function of temperature. Vapor pressure, temperature, in this case it's in atmospheres. but it's for several different compounds, and this is a semi-log plot because we have here just the normal x-axis and our normal units in temperature, degrees Celsius, but this is a log, the y-axis is in a log scale, so this is what we call a semi-log plot. And you'll notice that the lines are a lot more, they look a lot more linear or straight. And what this is showing us is the various compounds, how their vapor pressure changes with temperature. And particularly it shows us the ordering of different compounds. So for instance here, this blue line here is methyl chloride, and this red line over here is diethyl ether. And if we just pick a particular temperature, for instance, let's pick 10 degrees Celsius right here, we see here that the compound with the highest vapor pressure is methyl chloride, and then butane, and then neopentane, and then diethyl ether, etc., etc. When we see comparing different molecules like this or compounds, what we say is that methyl chloride is the most volatile compound here. And volatility is just a descriptive word that we use to say that something has a tendency to be in the vapor or gas phase. So in this case, methyl chloride wants to be in the gas phase the most out of all of these different compounds because it has the highest vapor pressure at any given temperature. So methyl chloride is the most volatile, and then we might say that, well, methyl chloride is more volatile than butane, and butane is more volatile than neopentane, and neopentane is more volatile than diethyl ether, etc., etc. And this again is because that the vapor pressures are higher for these compounds, and the vapor pressure gets lower as we go down the line here in comparison, so that the more volatile components have the higher vapor pressure. Now notice there's a few black marks here, black dots here. Well, that corresponds to when the vapor pressure is 1 atmosphere, and again, that's the normal boiling point of these particular liquids. And so to find them, we just find out where they cross up here. And methyl chloride, it looks like it's about negative 25, negative 26 degrees Celsius. For butane right here, it looks like it's just above 0 degrees Celsius, maybe 1 or 2 degrees Celsius, and we can go down the line all through here to find out what the normal boiling point of these various compounds are. Now let me just point out one more thing is that when I say the boiling point, I refer to the normal boiling point. The normal boiling point is the boiling point at 1 atmosphere. Typically the pressure here on Earth is about 1 atmosphere. The boiling point may change depending on the pressure. If we're on a different planet, let's just say I get in my spaceship and I go fly off to some other planet of the universe that has a atmospheric pressure of 0.5 atm. Well, if I'm on that other planet, the boiling points of my liquids change. So in this case, if I just read across here, the boiling point on Earth would be about 1 degree Celsius for butane. Well, it suddenly becomes a boiling point of negative 15 degrees Celsius on this other planet, whatever planet it is. And so the boiling point on this other planet would be along this line right here, because the atmospheric pressure of this other planet is different than Earth's. So just remember that when we talk about, oftentimes we say boiling point, we do mean at 1 atmosphere or here on Earth, but sometimes we call it the normal boiling point. So when we look up vapor pressure data for a particular compound, we can look it up, for instance, online, we can look it in books and so forth, and vapor pressure data is tabulated and so forth. To get vapor pressure data, people run experiments, and what they do is they take a liquid inside a beaker or some material in some container of some sorts, and then they simply measure the vapor pressure, or what's the pressure of the material above that liquid, and that's how they get the vapor pressure, and that's how we get these curves, for instance, of water. So this plot right here, I show you right here, just could be taken from, for instance, experimental data. Somebody could go into the laboratory and measure it. Well, we don't always want to have to look up on tables and so forth what the vapor pressure is of a particular compound, and so engineers, being what we are, have developed or tend to want to use equations. And so various scientists and engineers have developed equations to describe the properties of vapor-liquid equilibrium. And one such equation is the Antoine equation, which I've shown you right here, the Antoine equation. And the Antoine equation is simply the log of the vapor pressure is equal to A minus B over T plus C, where T is the temperature, and A, B, and C are constants or parameters. And so if you look in the back of your textbooks, for instance, it'll have tables of parameters for various chemicals for A, B, and C. So just an example here. Here I just looked in the back of the thermodynamics book, and it has these parameters listed in one of the appendix for the Antoine coefficients. This is for ethanol. So I have A, B, and C, these different parameters for ethanol that I can just plug into this equation right here to calculate the vapor pressure. And there's just a few caveats we have to go ahead and realize with this equation. One is these parameters here are unitless. They don't have any sort of units to them that we attach to. But we have to get the units right on the vapor pressure and the temperature. So for instance, in our thermodynamics book, temperature in this case, the temperature that we use in this equation that's been fitted with these parameters has to be in degrees Celsius. If we try to plug in Kelvin or Rankine or Fahrenheit into this equation right here using these parameters, we're going to get the wrong answer. So we need to make sure that our temperature is in degrees Celsius. The other thing that we need to pay attention to is the units on the vapor pressure, and in this case the vapor pressure with these parameters in this equation is in millimeters of mercury, or which is the same thing as torr. So if I use this equation here, again, whatever number I get out for the vapor pressure is going to be in units of millimeters of mercury, and the temperature has to be in degrees Celsius for this whole thing to be consistent on its units. Again, and the units are related to these parameters that were fitted. If we were to use different units, like if this was temperature in Kelvin, then I would get different parameters for A, B, and C. So these A, B, and C parameters only apply when these units are used. Now, one caveat I have to mention is that not all Antoine equations use the same units. So these are probably the most typical units here for temperature and vapor pressure, but these are not the only units that an Antoine equation might use. So I have seen sometimes Antoine equations where the temperature has been in Kelvin, or the vapor pressure might have been in kilopascals. Whenever you're dealing with Antoine equation, you need to clarify what the units of it are. Thankfully, in our thermal book, the units are told to us right where it describes all these different coefficients for the Antoine equation. So whenever you're using an Antoine equation, the source should tell you what the units are for the Antoine equation. The other thing is, this is in log base 10. Sometimes Antoine equations are in natural log, which is different than log for the base 10. And so it's just a simple shift between the two, but you need to realize what sort of log is it. Is it a natural log or is it a log in base 10? Because they'll give you very different answers, and they'll have different buttons on your calculator when you're calculating them, if it's log 10 or if it's natural log. And so this is probably one of the most common ways that we use to calculate vapor pressure of molecules or liquids. Again, we could look them up experimental data, but oftentimes it's easier just to work with an equation when dealing with the vapor-liquid equilibrium for a compound. So there we have it. There's our brief summary of vapor-liquid equilibrium for a single component system where we just have one chemical or one molecule.